In this video, we will discuss about Gibbs phenomenon. Gibbs phenomenon arises from the following question: how the Fourier series converge for a periodic signal with discontinuities? We know about the periodic continuous signals, but what about the discontinuous signals and how this Fourier series converge for periodic signals with discontinuities? Albert Michelson was a famous American physicist. He was studying the measurement of speed of light, and he was doing lot of experiments. So as a part of the experiment, that is to study the speed of light, he has made one device which is known as the harmonic analyzer. So that is known as harmonic analyzer of Albert A. Michelson. He created this device in 1898. So if you go to YouTube and search harmonic analyzer by Albert Michelson, you can see a video in which you can see how this harmonic analyzer is working, how it is drawing the signals with when we add the number of sinusoidal waves. All this you can check, especially in a YouTube channel called Engineering Guy. You can see this video. So I request you to go and watch the video how harmonic analyzer is working. This device will compute the truncated Fourier series approximations for values up to n is equal to 8. The truncated Fourier series means consider x of t as our signal and x of nt is the truncated Fourier series. That means we are trying to represent the signal x of t using a finite number. That is why this n is there. You are going to represent the signal x of t using a finite number of harmonic sinusoidal components. So that is why it is known as truncated Fourier series. We need to consider the complex exponential components from minus infinity to plus infinity. But we are not considering here. We are considering only finite number of components. So that is why it is known as truncated Fourier series approximation. And he created this device, and he observed that for many of the signals xn of t, that is the truncated Fourier series, is equal to x of t, that is the original signal. But when we try to draw the square wave, so you know that square wave is a signal with a discontinuity. We have seen this in the previous video, how to calculate the Fourier series for a square wave. And when we try to draw the square wave using this device, he obtained an important and surprising result. In the beginning, Michelson thought that there is some problem with this device. For all the other signals, it is giving the best approximation, but it is showing some surprising result for the square wave. Josiah Gibbs was a famous mathematical physicist at that time. He wrote about this issue to Gibbs. This issue was investigated by Josiah W. Gibbs, and he has reported his explanation, and his investigations on this issue is famously known as Gibbs phenomenon. And the formal definition of Gibbs phenomenon is this: truncated Fourier series approximation, that is xn of t. Truncated Fourier series approximation of a discontinuous signal x of t. So let us take the signal square wave. It is a discontinuous signal x of t will exhibit high frequency ripples and overshoot. So this word is very important. High frequency ripples and overshoot near the discontinuities of x of t. That is truncated Fourier series approximation of xn of t of a discontinuous signal x of t will exhibit high frequency ripples and overshoot near the discontinuities of x of t. So this phenomenon is known as Gibbs phenomenon. Let us check what is Gibbs phenomenon. Okay, now check this figure. You can see that this square wave, this is the square wave, is the actual signal we want. We are trying to create this signal using Fourier series. We are trying to approximate this signal using the Fourier series. So here you can see that when we are using n is equal to 1, means we are using only a sinusoidal component. So you can see the sinusoidal component is looking like this. And now look into this picture where n is equal to 3. That means we are using 3 sinusoidal components, and we are trying to create this square wave. So you will get a signal like this. So when we add these 3 sinusoidal components, you will get a signal like this. We can keep on increase n. In this picture, you can see that n is equal to 7, and you can see the approximation, that is xn of t. Xn of t is the truncated Fourier series. The truncated Fourier series is somewhat approximating the square wave, but here you can see that there are some ripples at the end. Now in this picture n is increased to 19, so you can see that it is almost looking like a square wave, but not a square wave, and you can see that there are some ripples. There are some ripples at the discontinuities. This is the discontinuity. Suddenly the value is increasing here up to this point, then again the value is decreasing. So there are discontinuities at these points, and you can see that the approximation xn of t is showing some ripples at the discontinuities. Using Michelson's device, we can go n is equal to 80. That is 80 number of sinusoidal components can be added to approximate the square wave. So here in this picture you can see that n is equal to 79. So we have almost reached the maximum number of sinusoidal components that can be added to create the square wave, and you can see that this wave is almost looking like a square wave. This wave is almost looking like a square wave, but there is a problem. So this is what Michelson observed. There are ripples at the discontinuities. So these ripples he has observed. For all the other signals, the Fourier approximation was almost looking similar to the original signal, but when he tried to draw the square signal, he observed that there are ripples or overshoot is appearing at the discontinuities. About this only Michelson wrote to Gibbs, and Gibbs made his mathematical analysis, and this phenomenon is known as Gibbs phenomenon. From the previous video, we have seen that a square wave satisfies the Dirichlet conditions. So in that case, xn of t, that is the truncated Fourier series, at the discontinuities should converge to the average value of both the ends of the discontinuity. That is what we have discussed in the Dirichlet conditions. So in that case, we can see that limit n tends to infinity, x of nt is equal to x of t. That is, when the number of components increases, number of sinusoidal components increases, the truncated Fourier series will be equal to the actual signal. But while doing the experiment, Michelson observed that there are high frequency ripples and overshoot at the discontinuities. This is what Michelson observed, and he also observed that the ripples do not decrease with increasing n. So when n is increasing from 19 to 25 to 79 up to 80 he can make. So when the value of n increasing, he observed that these ripples do not decrease. That is the main observation he has made, and Gibbs studied this, and he has shown that for a discontinuity of unit height, that is, if the height of the square wave is 1, the overshoot or the partial sum, so the sum at this particular area exhibit a maximum value of 1.9. So it will go up to 1.9. In other words, we can say that there is an overshoot of 9% height at the discontinuity. At the points, these points at the discontinuities, there is a 9% overshoot, or the partial sum, that is the sum of the truncated Fourier series is going up to 1.9 value. And also when n is increasing to infinity, the partial sum become compressed, but it is not disappearing. It is compressed towards the discontinuity, and the energy of the ripples become insignificant. But the important point is that for any finite value of n, so we have to notice this point, for any finite value of n, the peak amplitude of the ripples remains constant. When n is going to very large value, the overshoot is compressed, but for a finite value of n, we can see that the amplitude of the ripples remain constant. Remains constant at the value of 1.9, or we can see that there is always an overshoot of 9% at the discontinuity. And this phenomenon is known as Gibbs phenomenon. Thank you for watching.